And we're live, maybe? See. Is that way? Yeah, okay. Hi. Um, hey, we are doing day 9 of Advent of Code. If you haven't seen any previous videos, then go watch them. If you have, then join in. We are going to hopefully have fun and not suffer like yesterday. Yesterday, I wasted a lot of time trying to solve a very general case for a very trivial input. And that went horribly wrong. I wasted hours of my life, but then I didn't. So yeah, um, now we've got that covered. Let's actually dive into day 9. Okay, so garage maintenance. You ride the camel through the sandstorm and stop where the ghost's map told you to stop. The sandstorm subsequently subsides. Somehow, seeing you standing at an oasis. The camel goes to get some water, and you stretch your neck. As you look up, you discover that what must be yet another giant floating island. This one made of metal. That must be where the parts to fix the sand machines comes from. There's even a hand glider partially buried in the sand here. Once the sun rises and heats up the sand, you might be able to use the glider and the hot air to get all the way up to the metal island. While you wait, for the sunrise, you admire the oasis hidden here in the middle of the of desert island. It must have a delicate ecosystem. You might as well take some ecological readings while you wait. Maybe you can report any environmental instabilities you find someone to someone, so the oasis can be around for the next sandstorm-worn traveler. You pull out uh, your handy oasis and sand instability sensor. Okay. And analyze your surroundings. The Oasis produces um, a report of many values and how they are changing over time, your puzzle input. Each line in the report contains the history of a single value. For example, 0, 3, 6, 9, 12, 15, then blah, blah, blah. Okay, some numbers. Um, to best protect the Oasis, your environmental report should include a prediction of the next value. In each history step to do this, start by making a new sequence from the differences at each step. Um, if that sequence is not all zeros, repeat this process. Um, okay, so repeat the process using the sequence you just generated. Once all of the values in your latest sequence are zeros, you can extrapolate what the next value of the original history should be. In the above dataset, let's look at that. In the above dataset, the first history is 1367, 1369, 12, 15. Because the value increases by 3 each step, the sequence of differences of that will generate all threes. Note that this sequence has fewer values than the input sequence because at each step you consider, yeah, basically we're just taking a derivative. Yeah. Um, since the values aren't all zeros, you repeat the process. Wait, what? Note that each sequence has a few values. Okay, all zeros. Then we do another thing, which is, yeah, we do get all zeros. This means you have enough information to extrapolate the history. Um, visually, these sequences can be arranged like this. To extrapolate, start by adding a new zero to the end of your list of zeros. Okay. But the zeros represent the difference between the two values above them. This means there is now a placeholder sequence above it. Okay, A, B are like very, yeah, basically unknown variables at this point. Okay, you can start filling in the placeholders. bottom up. Then A needs to be the result of increasing by 3. We get 3. And the value to itself left. To its left, yeah. Wait, A needs to be, yeah. This wording is like not very helpful, but sure. A needs to be 3, basically, because, yeah, 3 minus 3 gets you 0. And then you can fill in B, which is basically just also increasing by 3 now, which is 15 plus 18. Yeah, 15 and 18. So the next value in history is 18. Finding all 0 differences in the second history requires an additional sequence. Okay, what now? This is the second line of the thing? No. We go for, yeah, we add 15 and 18. Then we add, where's this 21 coming from? Did we have a 21 before that? We didn't. We did. Okay, so this is the second line. Okay, so the second history requires an additional sequence. Okay, so we are taking the derivative once more, then we are adding everything up back again, then we extrapolate 28. Then for the next line, we need another kind of derivative, another derivation, and then we propagate everything back up. So we do that. We need to find, if you find the next value of each history, in this example, add them all together, we get 114. Analyze your OASIS report and extrapolate the next value for each history. What is the sum of these extrapolated values? Okay, so yeah. Okay, let's dive into that. By the way, this is obviously like very like doing the things in Python would have been so much nicer, but we are here to learn Rust, so let's Rust over this. So firstly, let's duplicate day 8, which not that, yeah, okay. Day 8. Let's duplicate that for day 9. And let's paste our own part 1 thing right here. And we do not know what our input is yet. We do know what our output is. It's going to be 114. That's going to be our base assertion. We do not know what part 2 is going to be, but we are going to paste the placeholder, which is this thing and an empty string. And apart from that, I think we can delete everything else from the previous day and start fresh. So we have all of our parsing code. So much stuff. And we want to probably do something here. Let's think about that. So firstly, we need to pass everything into vector. We can attach this to our main module. Oh, and we do need to run that as well, like so. So that's going to be day 9. And we are missing one more thing, which is to add this to our solution Xenon. Okay, so we've got this thing, and okay, I think we are good. We can start doing things. So day 9. So what does our input look like? It's basically an array of arrays. We could try to do that without actually, only by keeping walking the memory, basically. Should we do that? we can literally just walk the memory, and every time we just dive, we take two pairs. We all the time, like at no point do we need to actually allocate anything. I think we could literally just walk everything, take all the derivatives, bubble them up, and then just walk out with just a single number, and then sum that into the next round. Let's actually talk about that. Let's try to visualize that. So this is not probably the shortest path to solve this, but this might work. So if we've got 1, 2, 3, that's actually, let's 1, 2, 4, 5. And we would want to see what is the next value in this history. We would need to, first of all, take the derivative, which means that all we need is 1 and 2 at this point. And then we can carry that over, or I mean, we can walk one more character over and just keep that lying around on the stack. And that would give us 2. And then we could already subtract these because we can. That would give us 1. And that means that we are only, we can always subtract the last one. So we've got this thing. Now we are able to walk one more character on the input length. Yeah, that means that we are already done with these two characters. We basically just need to subtract everything. So here we've got another 1, and then we subtract these two, and we get another 1, and then we subtract these two, and we get another. Okay, so this can be solved recursively. Then what we would get is we need to firstly then we need to like output the plus. Once we hit 0, we know that what we need to do is we pad with an imaginary 0, which is very easily like so, and then we just need to duplicate this one, and then in order for this, and then we need to basically what would give us the 1 if yeah so if we have 1 here, what would give us 1? This difference, it is going to be 2. Basically, we just need to add 1 to whatever we've got here, and that would produce 5 plus 2, which gives us 7. So this is our way to walk this thing and do it without actually doing any allocations, or we could do like the full iterative approach. Not sure which one is going to be like obviously the iterative approach, which means we're only going to do like take the derivatives for every row is going to be a little bit more like, let's say, organized, but it's going to be more memory intense. This one is going to be more algorithmically intense, but like for my mind, but we're here to learn some new things, so let's try that. Okay, so now that we've got that covered, let's try to figure out how do we actually compute the next element. So let's do this as if we've got already a vector of ints, and then once we've got that formalized, we'll actually do the parsing and do that, I think, in a better way. Or maybe, you know what, because we don't want to do any allocations, we do want to actually do this algorithmically directly on the string input. Okay, so yeah, sure, whatever. That's going to be a to-do. So first of all, numbers. No, that's actually not correct. Okay, so we do want function predict next. That is going to accept an input string, and that's going to return us another actually U32 or something. And here what we would want is basically we've got let's map. We do want like to map something, and that's going to be a separated list, but we don't want to keep the list around because we are not going to actually we want so we want many one fold. Sorry, fold many. Yeah, okay, so we want to fold many one. Why is it saying LR? Oh, have a runaway a leftover test that is confusing Copilot. So for each list, how do we get? First of all, we need the actual numbers. So we've got fold many things. Okay, and here we've got what is it? It's going to be a U32 from non-complete blah blah. Yeah. So that is going to be our number. But it is going to be terminated by space, an optional space. So terminated by an optional tag space. Okay, and now we've got our numbers, and we do want our accumulator, which is 0 at before, and not XORing, because that's incorrect. But we do want to figure out what is the next thing that we want to do. So we've got our accumulator, and this claims that it's unhappy because this function might need to take some more things. We might not actually need more things. We just need to apply the input to it. And we've got a ref U32. Okay, this is basically, we are now streaming through the input. And now we need to figure out what's the actual thing that we need to keep track of, which is, if we go back here, we advance one character in the input. We need to basically produce, first of all, this is our accumulator. So the first character is going to always be the first thing. No, that's actually, no, that's the derivative. So we needed to know how do we produce this. We need to say, let's think about that like programmatically. We've got our previous character, we've got our accumulator, and we've got our current. So this one is going to be always current minus prev. So current minus prev. So this is going to be the first one. So if we actually like try to unroll this loop, so we've got that thing. Then when we iterate next, let's actually think about that. Okay, so we are here. Then we just initialize our accumulator with this one. We do that by saying accumulator equals to the current minus prev, and the previous one is 0 at this point. We can pretend that there's like a magic 0 here, and then just shove everything like so. Sorry, this is the one. That's so. Let's think about that, because we might want to see them as a window. That might be useful if we want to do that without like actually allocating anything. Is there a way to take windows on the input? Okay, we'll try to reason about that easily later. So this thing would produce so firstly prefetch. No, let's think about what else do we have on the, like, in terms of context here. We could recognize both things, and then we do know that like we could like look into the future without consuming the input. I think Nom has that feature. Let's try to figure out if this is what we actually need. Or maybe we just need two separate pieces of memory, which is the previous and the thing. Okay, so let's actually, we just need two ints on the stack. That is enough. So let's just have two ints on the stack. That would be good enough. So we've got this thing. We return 0, 0. Then we've got previous and what we are accumulating. Then we do need to return something. That something is going to be if the previous is 0, item accumulator. Otherwise, no, that's incorrect because it doesn't know anything about us at this point. So now that we've got that covered, we are basically pretending we've got always some previous number. Let's think about how would we actually do this. So we've got 0 and 1. That produces 1. How do we do this iteration thing? We need to somehow like linearize this walk. One, two. Wait. Okay. Let's literally look at this thing. So we are pretending we've got 0 and we've got a 0 around here. That's our accumulator. So this is the first character, which always produces. This is incorrect. We've got 1 here. Then do we always start with 0? No, we don't. Yeah, okay. Basically, that's okay. Could have been 0 anyhow. Doesn't really matter. So we need to find how do we initialize this correctly. We've got 0 here and we've got 1 here. Okay, that is incorrect because that actually ruins everything. Ooh, interesting. So I cannot like make numbers up. So in this case, if I cannot make numbers up, this is our actual like thing. So let's think about that. I mean, we could literally recurse everything, but that is just so annoying. We are guaranteed this would somehow work. Okay, we are not going to validate like anything here, so we are going to pretend this is actually going to converge on like a list of zeros. So oh, this is incorrect probably. Let's look at these things. It's always increasing, so that way there is no way that this is not a valid input. This can only be either 6 or something other. Yeah, basically this is now going to be 2, this is going to be 0, this is also going to be 0. And that thing is going to be -1. No, wait, what? Okay, we do need. Let's just use their example just to be sure that we're not doing anything wrong. So, but let's use the less canonical example. Okay, so we've got 2. Oh, yeah, 2, 3, 4, 5, and 6. And that is going to be 1, 1, 1, 1. That is going to be all zeros. Okay, so all of all the derivatives must be positive. Interesting. Um, that is actually very interesting because that means we can probably even infer that just by looking at the number, like what kind of polynomials the polynomial does that fit? But we're not going to do that, not yet. So you know what? Let's just do the iterative thing. I care not for doing this like efficiently for now. Let's just do this thing. So first of all, let's just do numbers, which is numbers. It's just going to be a function that accepts a string input. I'm like being pure and everything is just um yeah, I don't care about that. Let's just do this. Let's just use vectors. So we've got input numbers, iResult string. We are getting a vector of thing that's going to be terminated. No, that's incorrect. Just terminated by, so not many one, no, separated list. One, and that's going to be our separator, and that's going to be our thing. Okay, so we've got numbers. And that's a vector. And now that we've got our vector, we could actually try to predict next on that, but that's actually the problem. So that's going to be, let's actually just have all of the histories. That's going to be our vector u32, and that's going to be a separate list by new lines, yeah. And that's going to be an optional new line because we don't have one at the end. So optional new line. Yeah. So we've got our lists. So this is our histories, and we could try to figure out now part one. So we've got everything allocated. Let's actually, first of all, let's test that the number parser is actually working, just to be sure. So we've got test fn test numbers. Yeah, that's going to be the thing, and test and test histories going to be all of the thing. That's going to and that's going to give us, yeah, this thing. Okay, seems legit. Let's run these tests, and we've got very long build, but the number parser is okay, and the history parser is failing. And why is it failing? It's failing on separate list input empty string, and that's because we set optional new line, and it does not like that. It always consumes the optional. So that's going to be just a new line, and everything works. Okay. So part one. Let's literally have a function that's called part one, which returns just the output. So fn part one. That is going to be an anyhow result of string, and that's going to be so just okay, and part one to string. Yeah, seems legit. And our input is going to be let histories be this thing, fail to pass. Seems okay. And now we've got that covered. Part one is actually going to we do need our histories. That's going to return vec of u32, u32. Yeah, that's okay. We need to predict and then sum everything up. So let's try to do that. We've got histories for each one of them. We are going to fold because we are going to we will need to sum everything up. So we've got 0 as the thing. We could actually reduce because we do know that we are always starting with 0. So what should the function look like when we are reducing? We are reducing, so we are going to accept one history each time, right? Then once we've got that, I'm just gonna let Copilot like try to be very, very Copilot is bad. So histories iter. Oh, we forgot the iteration thing. Iter reduce. Okay, so we've got a vector of U32s at this point, and we do need to do something with them, which is to actually think about how do we sum things. So we've got let's just help our IDE because apparently it does not understand vec of U32s. And now we've got on number and everything should be working. So the walking through the history would probably be the same thing, but the predict function is going to be different. But we'll see about that in a minute. So we are going to walk through the history. So let's try to iter that. And we do need to do something, which is to look at that through a kind of window, take while, map windows. Ooh, map windows is interesting. Because for each window, we could like trickle down everything. Is that like a thing? Let's look at windows. What would that look like? Iter map windows. Non-fused iterator. Recently added. That's unstable. Oh, so let's not use this unstable feature. Um, chunks to owned. So here we can try to like do this fold and think about it. So let's add a to do here. And this one is well, expected U32, found vec option, unwrap, whatever. Histories reduce. Yeah, we'll just let that like compile away and that will be fine. So how do we actually predict 1, 3? So function predict next. That's going to get a vector of history. And we do need to like recurse a little bit here. So we've got just our vector. We are going to iterate over that, and we are going to we could literally take the derivative. So we could say let derivatives be iter reverse. No, I want these in pairs. Is there a way to take them in pairs? Rust. Just Google that faster, quickly. So Rust iterate pairs. So we've got step by. Interesting. But that is kind of like bad chunks too. But I want like overlapping pairs. Iter tools. Ooh, iter tools. Next tuple. So iter tools to the rescue. Okay, so let's use iter tools. So what do we got here? Do we got any reverse min max fold batching chunks window? diff. Interesting. Multi unzip, partition, peek, nth. So peek nth, let's look at the definition of peek nth. A drop-in replacement for ether peekable. So that is operator adapters are lazy and do nothing unless consumed. Must use. The peek nth for more thing, blah blah. Add then a peek that returns an optional to reference the next element. So we do know when we've reached all n. So we could do that. I mean, this is obviously the more inefficient route, but let's try that, and then we could try to rewrite that if I'd have like patience, basically. So we could dot peekable. Peeking take while. So we've got that. I'm not sure how do we use it, the peekable thing. So this is not actually. You know what? This is I'm still not sold on this thing. So dropping window, tuple windows. Let's look at that. So return a window. Okay, that's it. Okay. That thing looks very good. Yeah, if we take a range 1 through 5, then we get all the windows. That's very good. Okay, so tuple windows. Seems like the right thing. So histories. Let's look at that. Not histories, but oh, sorry, that's a to do. So predict next. This is going to accept exactly one history, and we are going to say history.iter.tuple windows. And it says it does not know what tuple windows is. Interesting. Do we need to go like so? Do we need to import that somehow? On any iterable. So okay, so it is recognized. So we've got tuple windows, which gives us circular tuple windows. Interesting. Not sure what circular means here, but anyhow, this is going to be now we can now that we've got these pairs, we could try to fold each pair basically. Okay, that is probably the way to go. So we've got so we've got our pair. We are folding this. We start with an accumulator of 0. Hopefully, after we are done, we are done with like trickling everything down. Could try to figure out. By the way, are we guaranteed like that we won't see any zeros before that? No, we are not guaranteed that. So how do we know when to stop? We don't. We need to basically dive all the way in. Do we need the index and the length? Maybe think about that. No. Okay. So we've got these pairs, and this thing is going to be okay. So we've got these things. We go with I32. Yeah, it does not recognize, like our IDE does not recognize anything because apparently the import of the U32 parser is confusing the IP. So let's actually call that U32 salsa. And then we just need to fix that up right here. And everything else now would have like proper types. So tuple windows, no method, yeah, on struct, that's okay. So that should be b minus a, basically. This is all the time. This is like the derivative. But we do want to keep track of something, except for the derivative, because we don't want to just do this. We don't want to sum things. So instead of summing, we could try to, let's walk this very, very slowly. So we did this, and then we've got some number. And then we need to keep track of that number. We have to keep track of this number. Then when we've got to the next thing, we could already reduce that. But then when you get to the next thing, we need to reduce like more times, which means that we do need like some kind of like recursion, basically. How do we know how deep do we need to recurse? We don't. I mean, until we've reached zeros, but if we always have zeros, interesting. So basically, let's look at that a little bit. How could we know what our result is going to be every time? If we look at this, so we've got this pair. We are right here. Our accumulator is like, our state is basically 0 at this point. Okay, no, never mind. I'm like always trying to go back to the iterative solution without like doing the recursion. Let's just do the recursion. So we do this and we don't need to fold. We basically just need to map this. So that's going to be map, no function, no accumulator, no, yeah, basically all of this. And here we've got what is this? That's going to be our diff. And then once we've got our diff, we do need to collect that. Do we? I mean, it could be an iterable. I don't care. We don't have to allocate that. That might actually be like the way to do this correctly. So this could be an iterable. So iterator, I32s. Um, what does this look like? This one returns an iter of something t. So if we go with iter, is that a thing? And it says the trait that allows what? I don't care about that. So just history tuple windows. Okay, so I think that is actually a thing, and it might be wrong. Okay, so my code intelligence is like completely wrong. So let's not over optimize things. So for now, collect, and then we can think about being lazy. So we've got collect, and that's going to be a vector of same thing. So basically this. And that thing is going to be, well, it's b minus a, which means that maybe keeping a sign is not completely insane. So let's do that. I'm not sure we should see negative numbers. Actually, you know what? Let's pretend we don't see negative numbers at all for now. And we've got our diff match on, wait, we've got if diff all zeros, all x equals zeros, do something, otherwise something else. So if diff all zeros, we do want to basically, okay, if we're all zeros, we are not recursing anymore. We are just returning the last element. That's the only thing that we need to do. So that's going to be, is it the diff that we want to return, or this is the diff? So not the diff, but we want to say history dot last wrap clone, sure, whatever. Else, we want to say predict next diff. We borrow the diff, yeah. And that is now, that means we are recursing every time. This is going to be shorter, hopefully, with like every time a little bit shorter. And that needs to be actually not just last, but that needs to be diff plus last, because we are going to, yeah, sum everything. So diff plus last. Is that true? Let's think about that. Cool. So we basically need to say, instead of, we do need to append to the diff. Interesting. So, or append. I mean, we just need to return like plus, basically. So something plus thing, which is to say history dot last plus something. So let's try to reason about that shortly. So we've got, this is now our history, 222. We've got diffs of 2 zeros. And then we say, if diff is all zeros, then we do need to say we pad with another zero. And we basically say what would give us that, and that is exactly the same number, which means that we just return this plus last. And then we bubble this up to the next level, which is basically we say sequence, so history plus whatever the diff plus last is. So we just need to say, well, history plus last, unwrap clone, whatever, plus this thing. And that is always going to give us the predict next on the diff. So yeah, this is now going, we now have our stop condition. I mean, also like if the diff is obviously of length 0, that would also stop, but let's see if this actually like does the thing that we expect it to, which is we've got the numbers tested. So now we could say test predict. So 136 is actually going to predict next. That's going to be, well, no, that would be 9. That's the next thing that we expect that to be. Then let's run that. It says vec apply fix part 1 history. So what now? Function defined here, part 1. Ooh, histories. And that is going to be a borrow. Yeah. Okay, so our prediction worked for a very small case. Let's actually give it a heftier case, and that is going to be this vector. So let input be all of this vector, and vector be 18. That is correct. And now the next one is going to be actually a little bit harder, which is let input the vec of not 18. No, no, no. Let's actually take this one. So oh, come on. You know what I meant, Copilot. Thank you. And the expected is, well, is it 60? 68. So the expected is going to be expected equals 8 and predicted expected. Now we've got cannot reassign let. And that is working. So our prediction is working. Let's just fix up that typo. Predict. So this thing is working. We could try and make this completely, instead of like doing this collect and accepting a vector, we could literally accept an iterator on both ends. And then we don't need to do any collection. We don't need to do any allocations for now, but this is good enough to actually just do this thing where we say now part one is just going to say histories map predict next. What is this? And Copilot, what are you fucking doing? So we are going to reduce that. So just that's just going to be a reduce operation, and that is going to accept an accumulator. No, not an accumulator. Wait, what? So we got histories, and for each one of these histories, we are going to reduce each of them into. Oh, let's actually literally map on this thing and dot sum. Yeah, so map sum should work, but we could literally reduce that instead of like mapping and summing, which is basically same thing. So yeah, reduce. Reduce takes a function that accepts two things. One thing, how's that? What's the exact API? Accumulator and the item. So ACC, yeah, ACC and our history, and that is going to be. Is there, by the way, like a map reduce thing? Map reduce. I mean, it is exactly what we want, but sure. So we just return ACC plus predict next on the history. And one of them says option. Interesting. So, or option is here. What is that? Predict next returns a thing, and this one is a thing. So this one is reducing on not the right thing. Oh, I see. It's reducing on a vector, not on a U32. Why is that? So yeah, let's fold, because apparently this one does not know what we want is a U32. Okay. There's no need to unwrap this. That's nicer. So I think that should do part one. So let's run the test for part one. And we are passing the test. That's very nice. Okay, so we've got all we need to run this on the actual puzzle input. We paste that into our day. Always select open file, please. Then we duplicate this thing, we say day 9, paste our input in. We do have negative numbers, which means that we need to change everything to I32s instead of U32s. Well, too bad. Sure, whatever. So first of all, let's just optimize some inputs. Let's take an I32 parser. Let's I32 as I32P. Let's delete that, see where we've got some errors, and start propagating everything back. So where's our I32P? Yeah, that's going to be, well, type number for today. I forgot what okay, so type reading basically. That's going to be an I32, and type readings, that's going to be a vec. Okay, and let's just figure propagate these changes together. So this is going to be a vec of readings, or just readings actually. Readings. That's going to be a vec of readings. And this one is going to be part one. That's going to just be the sum. That's actually a number. And that's going to be an I size, just because we don't know anything about that. And predict next is actually going to be predict next reading. And this is going to be readings, because we could. And that's going to be also a borrow of readings. Anything else that we need to fix? This one also, this needs to be a readings vector. And looks like we are still found expected I size, found U32. Okay, so this one, predict next. Okay, let's try to pretend this is a reading as well, and that is going to bite us in the ass if numbers get really big, but we do know what to do with that. So firstly, okay, we've got things still tested and everything. We haven't broken anything in terms of types. And let's figure this out quickly. So we do want to just edit this configuration and insert the 9 here, apply, run. That thing is going to run and give us some solution. The solution, does it warrant us a gold star? See? Yay, 1 gold star. Yay. That's the right answer. And let's continue on. Of course, it would be nice to have even more history included in your report. Surely it's safe to say that we just it's safe to just extrapolate backwards, right? For each history, repeat the process of finding the differences until the sequence of differences is entirely zeros. What? Okay, so for each history, repeat the process of finding the differences until the sequence of differences is entirely zero, rather than adding a zero to the end of. Okay, so now we are. You should instead add a zero to the beginning of the sequence of zeros, then fill the first value in each previous sequence. So we've got our histories, adding a new value to the left of each sequence. Okay, so what is the sum of the extrapolated? Okay, so we just need to reverse everything. So let's try just doing this very, very, very crudely. We've got part 2, which is we look at the histories, and for each one of these histories, we reverse it. So rev and this thing is now the spot where we say, well, let's try and actually make predict next an iterable instead of vector. So this is going to be, well, not, let's have a reading iter. That's going to be an iter of reading. And then that says dying. So an iterator of item. Why is it going for TQDM? I'm not happy with that. But so if we go for stud iter, is that a thing? Collections. So if we've got any kind of like vector, we say iter on that. What does that return? This returns an iter new, and this iterator is from stud core slice. Interesting. So let's try to import that. So yeah, okay. Use third slice iter. Yeah, yes, please. Then it says we need some lifetime for that. So let's just add a lifetime. And our reading is going to also have this lifetime. Oh, we don't need to. Okay, so we've got a reading iterator. So let's try and figure this out now. So we've got this iterator. We've got a reference to an iterator. Oh, we could borrow, actually. We could literally borrow. So that's going to be a reading iter. Then we don't need to iterate here. We don't need to collect. We do want this to just be the thing, and then we could say pass and the thing. Okay, so it says expected reading iter found tuple windows blah 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 blah. So how can we make this a generic iterator? Because I'm not sure. Okay, so this is where probably first of all iter on the same thing. So this is going to be no, that's actually going to be a reading. That's just the one. Just because I don't want to collect this. This is basically the whole thing is I just want this and that to be the same like input without actually doing the collect. But we could avoid all of this typing gymnastics just to do this. But we could say something like where, right? I think where is the um um so let's actually learn how to use functions that accept iterators. So Rust iterators. Iterator processing a series of events with iterators. So I want to look for the net where thing. So where? Okay, no type hints for us right now. Iter map blah 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 collect. So this is probably not the right way to do this. We need to think about that. So we say this thing where cannot find type in the scope. So let's just do like so, and we say iterator, and that is going to be where I is iterator over a reading. And I think that might be the way to do things. If I only knew. Okay, and that is, let's look at that. It says expected ref to something found iter reading. Change the parameter of history to take iter reading. And is that not correct? Does that need to be we do want an iterator of things. Let's try to compile that and actually see what we've got. Okay, so it says expected this, found an iter of i32s, and it says found structs less still slice. So it says dot fold dot iter. Ooh. Wait, what? Oh. History dot iter. Wait, let's try to compile that again. So apparently, can we just pass that like so? And it still says that the is not an iterator. Try calling into iter. Into iter. Then says try removing the method called predict next. What? Oh, we need to borrow this. Or you know what? We do want to pass in the actual iterator. We don't want to pass in the borrow with this thing. So iter expected iter of some lifetime I32 to be an iterator that yields. Oh, it yields references to I32s. Interesting. So that could be the problem. This needs to be just a reference to, and then it says that reference without explicit lifetime is not good. Okay, so we do need like a lifetime here. Oh, it might be actually this thing that has a lifetime. So for lifetime A and ref A reading, then it says binding associated for item references tick A, which is not bound to the trait input type. Okay, so tick A, shadows lifetime. And it says that no method iter found on struct map. Diff iter, yeah, we don't need iter anymore. We can just say all because it's already an iterator, and this is an I32, so we can just use that. Then it says lifetime required by this bound. Right. So we are passing ownership if diff all, and then it says make diff mutable. Why do we need to make diff mutable? Cannot borrow immutable local diff as immutable. Why do we need mutability here? Expected ref I32 found I32. So this one is actually, let's take a reference in that. And that now is, yeah, now it's claiming that we do want install that. Then it says, yeah, okay, so we create a temporary value, but we do want to pass that. So in order for this to work, we do need for this to be either, it needs to support both references and not references. Let's think about that. So let's go with just the readings. Click next. And then we don't need the lifetime. This one is okay, I think. But we do need to pass in concrete values and not borrows of values. So this history thing, like of reading, so how can we pass in the right thing, which is, yeah, it says this is now borrows for some reason because we're pointing back to the memory that is owned. So let's think about that. So iter into owned, maybe. And then it says, no, it's still references. Map, no reversing. Then it says, ooh, yeah, okay, so we are now here. We just need to map that also to an actual thing, which is map, yeah. Okay, and then it says cannot borrow diff as mutable. Why is that? This is not a mutable. Oh, because iterators are mutable. Because they are consumed. Interesting. So how can we do this correctly? So we want to consume once and use twice. Or do we? So if it's all zeros, we want to firstly, okay, so we've got last clone. Damn it. So we've got our map. Yeah, I'm going to say fuck that shit. Let's collect everything. That's going to be dot iter. And that is going to just be readings. And that is not going to be, we're not going to do type gymnastics. And we are going to definitely use collect. So we don't need to do anything fancy here. We just say we pass in the history. And here we also pass in the history. We just need to reverse and collect that. So reverse, collect. Then it claims that it's unhappy about this thing. Why is that? Because we need to borrow probably. And borrow as well. And that is going to be a borrow of readings. And that is going to be also a borrow. And then it says iter rev ref blah 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 cannot become. So this thing is going to be, yeah, we need to iter. Let's map that into actual things and then collect them. So this is a reading. Right. The method tuple window exists for vec, ref of vec, but its trait bounds are not satisfied. What are we missing? This already worked, so like something very close to that already worked. So we've got our diff. Let's literally have that as a readings thing. So we say, oh, sorry, that iter tuple windows. Then we do need to get that back into a reference thing, dereference. Okay, so we've got part 1 working. Now let's go for part 2. So part 2 is now the same thing, but we expect to produce the number 2. So part 2, that's our assertion. And let's go back to our run function, and we do need to say part 2 histories ref string. So all of this crap, and we've got some number. And this number, we just plug that right here. We haven't run the tests, but yeah, I was fairly certain everything is just work. Okay, so we won. We're done. Only took 1 hour and 13 minutes. Most of them I wasted on just thinking about doing this very optimally and then just doing the naive solution, which is just good enough. So yeah, hope you enjoyed this one. It was quite more simple than yesterday, or but I don't know. Not as easy as day 6, but quite easy. And I'll see you tomorrow, and hopefully we'll learn some new things together. Bye bye for now.